Hi friends, welcome to my channel TechnoBuzz. In this video, I will discuss multiphase simulation using OpenFoam12 with object rotation and oscillation. If you are visiting my channel first time, please do like, share and subscribe. Now let's start the video. So in this video, I will discuss how to set up a multiphase simulation with object rotation and oscillation. So let us see the route map. First, I will explain the objective along with a brief introduction on multiphase modules in OpenFoam12. Further, I will discuss and show the geometry considered for this simulation. Next, I will explain the OpenFoam12 folders and files needed for multiphase flow simulations. I will visit each file and explain in detail. Next, I will explain the files needed to enable dynamic mesh for rotation, oscillation, and translation. Finally, I will launch various simulations and present the animations. So now let's dive into the first step and discuss. It is a proof of concept simulation of dynamics of rectangular capsule with multiple degrees of freedom. In my earlier video, I used a simple domain with an object and demonstrated conjugate heat transfer simulations. The link of this video is given in the description. The same geometry without source and sink is used in this case. The capsule is half filled with a solid object located in the center. This is the rectangular capsule created in Salome. To initialize the water region, we need an STL file. So this is the water region at the bottom of the capsule. I considered half-filled capsule. Now, to enable the dynamic mesh region for rotation and oscillation of the obstacles or object, we need to create non-conformal dynamic boundaries. So for this, I created a cylinder. I created a cylinder here. Based on the degrees of freedom of rotation and oscillation, a suitable shape like cylinder, sphere is to be selected. In my simulations, I considered rotation and oscillations of the solid object over a z direction, and hence I create a cylinder along z axis. So I change the color here for clarity. So this is the cylinder, you can see. Further, the solid object is created. Further, the solid object is placed in the center of the capsule within the cylinder. So this is the solid object created. I remove the capsule, water body. You can see now the cylinder. Now you can see the cylinder with the solid object within it. The dynamics considered in the simulation are rotation and oscillation of complete geometry, that is the total capsule and the solid object as a whole, as a single object. The dynamics considered are rotation and oscillation of complete geometry, capsule plus solid object. In the second simulation, rotation of only solid object with stationary capsule. In third simulation, oscillation of only solid object with stationary capsule. These are the dynamics considered, and the modules of OpenFoam12 which are used in this simulation are mesh moment and multiphaseVOF. Let us dwell briefly on multiphase modeling. Generally, immiscible fluids are modeled using multiphase models. Fluids that are completely insoluble in each other, such as water, kerosene, water, oil, etc., are immiscible fluids. There are two types of approaches: Euler-Euler approach and Euler-Lagrangian approach. In Euler description, the fluid is considered as continuum and modeled using Navier-Stokes equations. In other words, Eulerian modeling imagines the flow as seen from a fixed point. Lagrangian description imagines the flow as seen from a boat, that is, each individual particle trajectory is tracked. Both the models have their own advantages and applications. There are three models in Euler-Euler approach. The first one is VOF model, volume of fluid model. This is a surface tracking approach and applied for two or more immiscible fluids. This model is mainly used for tracking the interface between the fluids. This model uses one set of Navier-Stokes equations along with an additional continuity equation to account for the volume fraction of the second phase. So for n number of phases, including the primary phase, n minus 1 volume fraction equations are to be solved. Right. So the volume of fluid model can be used for modeling free surface flows, sloshing, dam break, etc. Second model is Eulerian model. This is the most generalized form of multiphase modeling. In this model, each phase is modeled using one set of continuity and momentum equation. So, for n fluids, n set of Navier-Stokes equations are used. In thermal hydraulic simulations involving multiple phases, a temperature equation is also solved for each fluid with proper thermal exchange coefficients. Phase coupling is very important for exchange of mass, momentum and temperature between phases. This is achieved by coupling coefficients which essentially appear as source terms in the equations. Wide ranges of applications are there like fluidized beds, particle columns, multiphase invisors, bubble columns, etc. The third one is mixture model, which is also called drift flux model. As the Eulerian model is generalized and most detailed modeling, it is computationally expensive. In most industrial applications, simplified model help to qualitatively predict the physics. So drift flux model is one such simplified model. This model consists of one set of Navier-Stokes equations with mixture properties and uses experimental correlations for relative velocity between the phases. It is essentially a two-fluid model. This model can be used in particle-laden flows, bubble flows, sedimentation, and cyclone separators. Finally, in flow scenarios where interfaces are not well defined, like in dispersed phases, homogeneous mixture model can be used. In this model, the relative velocity between the phases is neglected, and it is the most simplified model that can be used based on the requirements. This is briefly about Eulerian approach. The second approach is Euler-Lagrangian approach. This model is used in multiphase flows where the volume flow rate of the secondary phase is around 15 to 20% of the primary phase. The primary phase is considered as continuous phase and modeled using Eulerian approach. That means one set of Navier-Stokes equations are used to model this phase. Now, consider two fluids. If the volume fraction of the second phase is around 15 to 20% or less, then this fluid ceases to be continuous and breaks into parcels of droplets. In other words, it loses its continuity. In such scenarios, the second phase is modeled using Lagrangian approach, considering it as discrete phase. The mass, momentum and energy exchange between the phases is considered using source terms. There can be two-way or one-way coupling. Some of the areas include sprays, fuel combustion, particle-laden flows. Let us explore the multiphase modules in OpenFoam 12. Multiphase WOF solver. Different variants of WOF solvers are listed here. Both incompressible and compressible versions are available to cater the needs of various applications. These versions can model thermal hydraulics with turbulence in steady and transient mode. The second one is multiphase Euler, the most generalized multiphase Euler model. In OpenFoam 12, this replaces the multiphase Euler foam of earlier versions. It is robust and capable of solving multiple fluids phases with the reactions, heat transfer and boiling. So with this brief introduction, let us jump to the second step and explore OpenFoam folders and files and discuss how to modify or add files to activate the multiphase module. In step 2, let us see the OpenFoam 12 folder structure and the required files in each folder for activating multiphase module. The best way is to start with any relevant tutorial case which includes multiphase and dynamic mesh. So I have selected the case of tank sloshing. The path of this tutorial is given here under. I launched the case directly and created the animation. The capsule is a closed domain and partly filled with water as seen. There are no sources and sinks, that is entry and exit boundary groups. The capsule is subjected to oscillations in multiple directions. Now, let us browse through the folders. The folder structure contains following folders: 0, constant and system. The other folder, Gen 6 DOF, is related to dynamic meshing. Let us explore each folder. First, let us explore folder 0. This folder contains 3 files as shown. These files are related to boundary conditions for the two fluids, water and air. The file U looks like this. In this case, only wall boundary condition is specified. We can add velocity inlet, pressure outlet, and other boundary conditions as required in different cases. Now the next file, P_RGH. Generally, pressure boundary condition is specified in P file for single phase flows. In gravity driven free surface flows, the pressure boundary condition is specified in this file P_RGH. Alpha.water. This file contains the phase volume fraction. When we solve for two phases, water and air, equation for the phase volume fraction of water only will be solved. Hence, in this case, phase fraction of water is specified in this file. Now let us explore the folder constant. In this folder, we find the files containing the input specifications of gravity, momentum transport with input for laminar or various turbulent models and fluid properties. For multiphase flows, The physical properties of multiple fluids are provided in this folder. Added to this, the details of dynamic meshing are also provided here. Now let us explore each file. Physical properties.water. The physical properties such as kinematic viscosity and density of water are provided in this file. Physical properties.air. Similarly, kinematic viscosity and density of air are provided in this file. The next file, phase properties. In this file, the list of fluids and corresponding surface tension between fluids are added. In our proof of concept case, we use water and air as fluids and surface tension is assumed to be 0. In momentum transport file, as already known, we specify whether the flow is laminar or turbulent. If turbulent, then we add specific model and accordingly we need to add files related to K and epsilon etc. in folder 0 as we already know. Gravity file, as known, acceleration due to gravity is provided in this file. The file dynamic mesh dict. As told, this file corresponds to dynamic meshing module. This file activates dynamic meshing module, or in other words, it activates the motion solver. The solid body motion solver facilitates various dynamics such as rotation, oscillation, translation, multi-direction oscillations with various degrees of freedom. I will explain this in next step 3. The motion solver also facilitates to read the oscillations or rotation data from an input data file. 6DOF file. This is a data file. We can give any name here and the name has to be given in the dynamic mesh dict file. This is the data file to specify mesh movement, that is rotation, oscillation with multiple degrees of freedom. In this file we can see here the first column 0, 1, 2, 5. These are the data corresponding to time. In the second part, these 3 columns correspond to translation in all the 3 directions. And in this part, these 3 columns correspond to rotation in 3 directions in terms of omega. Now let us explore the folder system. In this folder, most of the files are known. You may see my earlier videos. There are 2 important files which we need to understand. They are create baffles dict and set fields dict. Now let us go with the file set fields dict. This file is needed for multiphase flows using VOF module. In this file, we specify the initial condition for the phase fraction of water. This file contains 2 blocks, default field values and regions. Default field values and regions. In default field values block, we initialize the volume fraction of water to 0. This means the whole domain is initialized with 0 volume fraction of water. In other words, the whole region is filled with air. In the second block, regions, we specify the regions in the domain where volume fraction of water is to be 1. For this, there are 2 options. In the first option, we define the water region by providing an STL file. This STL file should be saved in the main working folder. Now here to define the STL file, we use this option surface to cell. In the second option, We define the water region by specifying the coordinates as shown using box to cell option. This is the simplest option available, and if we want to provide a water region with complicated domain, we can use STL file. The file create baffles dict is needed for dynamic meshing module. This makes the internal faces between the stationary and rotating zones into boundary faces without duplication. In the present case, the zone within the cylinder is the rotating region as shown in the adjacent video. The internal faces differentiating the cylindrical rotating zone and the stationary outer zone are converted to boundary faces. Finally, let us explore the folder Gen6DOF. This folder contains the C file with this file name Gen6DOF. It is basically a C program to generate sinusoidal profile and save the data to an output file with the same name Gen6DOF. Once this file is compiled with command wmake, a data file with the name given in C program is saved to the folder constant. Now let us open the data file and check once. This is the data file in the folder constant. So this is the file. As explained earlier, the first column contains time data. The set containing these three columns contains the translation data in three directions, and the set containing these three columns contains the rotation or oscillation data in three directions in terms of omega. The first number 100 corresponds to the number of time data up to here. I make an important point here. We have to compile the C program to create this data file. I have a workaround idea to bypass this compilation. We know that the data file name 6dof.dat is specified in the file dynamic mesh dict. We can open this file. So here the file name is given. The standard solver executable reads this file and access the data from the data file. So this means we can directly modify the data file with our required data, or if we need to provide huge data using a profile equation, then we can write a Python or C script separately and save the data in required format. Hence, this idea bypasses the requirement of local compilation, and further we can delete this folder Gen6DOF from the working directory. Now let us go to step 3. Now let us briefly explore the dynamic mesh options. The parametric definitions for solid body motion are listed in this link. However, the code block for 6 degrees of freedom motion given at the link will not work in OpenFoam12. For this, one may have to check the tutorial case which I considered for this case. The file dynamic mesh dict in constant folder contains the code block as shown. In this block, the first option is type, so it is a motion solver. Then the motion solver library is to be added here. and then the motion solver is solid body. After that, the parameter definitions for different motions can be added. The different motions considered in the current simulation are 6 degrees of motion using data file input, then rotating motion using syntax and data file input, oscillating rotating motion using syntax and data file input, and then translation. For translation, only the whole body translation is possible using the data file. So the file dynamic mesh dict looks like this. Here, as I explained, type is motion solver and the motion solver library is added here. The motion solver is solid body. The first parameter after the basic block is select, where we give all. There are different options available here, that is all, cell zone, cell set and points. If we give cell zone here, then for cell zone we have to write the name of the cell zone. Then the solid body motion function is 6 degrees of freedom motion, this one. And here we give the center of gravity, the coordinates of the center of gravity. And this is the translation motion table. So here we are giving the table and the link of the data file is given here. So using this data file, we can give all these motions directly. However, if we have only rotation motion for a part of the object, then we can do like this. A simple syntax is given here where we specify the cell zone, cylinder, and then we give rotating motion. Here we give the origin of the rotation and axis over which the object is going to be rotated, and the angular velocity omega is given. So in this case, only that object which is to be rotated will be directly rotated. So here we give oscillating rotating motion, and here we need to provide origin, the center of point of rotation, then axis, and then amplitude and omega. Taking the amplitude data, it will oscillate over the axis. However, it may be noted that we can use the data file to specify all these types of motions. Now that we have explored all the folders and discussed each file in detail, let us start setting up the current POC case. In the current case, a closed manifold object is centrally placed in a rectangular capsule. The object is enclosed in a cylinder and the capsule is partially filled with water. This is the capsule outer wall where wall boundary condition is specified. Preferably moving wall boundary condition is specified. Then the object which is placed inside the capsule is considered to be a wall. So for this object also a moving wall boundary condition is specified. Further, as I have explained earlier, we have created a cylinder to create the interface boundaries which differentiates between the stationary and the rotating mesh. We need an STL file to initialize the water region. So this is the water region in the domain. Let us see the operating conditions. Water and air are the working fluids. Gravity in y direction is considered as the domain is created in that way. The flow is considered to be laminar and the surface tension between the fluids is considered to be 0. Now I have updated these operating conditions in the files and placed the STL files at relevant directories Let us explore the files in the working directory and launch the case. Now I will browse through each folder and show all the updates which I have made. Now let us start with the 0 folder. So in this folder we have 3 files. Let us open them. As we are considering laminar flow, K and epsilon other files are not present here. Now let us open these 3 files. The first one is U. So here we see there are 2 boundaries, wall and object. In P underscore rho GH also we see wall and object, and here we have given fixed flux pressure at both the wall boundaries. Then alpha dot water also, both the boundaries are updated and we are giving here type as 0 gradient. In U we have given moving wall boundary condition and the field is initialized with 0. Right. Now let us explore the second folder, constant. In this folder, the folder tri-surface contains all the 3 STL files, capsule, cylinder and object. The 4th STL file for water region should be placed in the main working directory. Okay. Let us open these files and check. So first we go with dynamic mesh dict. So here you can see in this simulation I am considering the whole body oscillation. So here the parameter select is all and the cell zone is also all. As I told, there are other options available, all, cell zone, cell set and points. So the center of gravity coordinates are given here and we are giving the data file as input here. So this is a link for the path for the data file. Now this is the data file. Let us explore this data file and see. Here in this there are 77 data points are given. The first column corresponds to time. We are not giving any translation here, so all the translation data is 0. In the rotation block, we are giving rotation in x direction. So the omega values are updated here in the x direction. Initially from 0 to 10 seconds around, a clockwise oscillation will be there up to 50 degrees. And then from there, from 10 seconds onwards up to 20 seconds, I have given reverse oscillation. So here the angular velocity will reduce. Then from 20 seconds onwards, I am giving omega in all the 3 directions. So this is all about this file. Now gravity, as I have explained, gravity in y direction is given here. Now let us open all these 4 files. So momentum transport, as we are considering laminar, the laminar is written here. Then physical properties for water, here we are giving the kinematic viscosity and density for water. Then for air also kinematic viscosity and density are given here for air. So here the number of fluids are to be updated. So there are 2 phases here, water and air, and the surface tension is specified as 0. So this is all about this folder, constant. Now as I explained earlier, there is no need for us to keep this folder, so we can delete it. I'm just keeping it as this, but we can delete this. Now go to system folder. Let us open all these files. So control dict, here the application is foam run. Incompressible WOF is a solver used, and then we are giving the start time. Here the start time will be 0 and the end time is 30 seconds, and delta t is 0.01, adjustable time step, and this result save interval is given here 0.05, and all other things are same and no need to change here. The main thing is block mesh. Based on the outer dimensions, the vertices are specified here, and the a uniform mesh with 25 cells in each direction is specified in block mesh. So in this file, surface features dict, we have to add the STL files, capsule, cylinder, and object. All the three files are added here. Then in this snappy hex mesh dict file, we have to add the geometry details. So here the geometry cylinder is added here, and then capsule, and I have added object. Apart from this data is same, no need to change. I have changed number of cells to 2 here. Then this is as it is, and you can check all these parameters in my earlier videos. So for surface based refinement, I am adding here cylinder, capsule, and object. So all other things are same. One may refer my earlier videos to see how to update this file. Now let us go to set fields dict. In this file, we have to specify the air and water regions. So the default region is air. Here we have updated the alpha water volume fraction as 0. Now in the regions block, we need to add the file for water region, that is the STL file for water region is added here. And now here, this is the outside point. We need to specify some point outside this water region and include that is false. Include inside is yes, because the water region should be inside this STL. So here we specify yes, and include outside should be specified no, and user surface orientation is true. If it is false, then some surface orientations will not be considered properly. So it is better to set it true. And the near distance is -1. I played with this value, but there is not much change seen, and curvature is 0. Now in field values, we are initializing the alpha water to 1. So this is all about this file set fields dict. Now this FV solution remains the same as earlier, no need to change. You can just use this file as it is. No need to change the FSPMs also. And then we have decomposed pair dict. No need to change here. This is for parallel processing. I use 2, but I am not running the case in parallel mode anyway. Then we have this create baffles dict. This is very important because here we need to create the interface boundaries for the cylinder. So here we are giving the zone name as cylinder, and the patches are given here. With this we create the interface boundaries. So this is all about this folder system. Then we can delete this Gen6 DOF file folder. I delete it. Fine. So we have checked all the files and updated all the data as needed. Now let us launch the case and check. Simulation 1, Capsule Oscillation. Here, multi-degree oscillation of the whole capsule along with the object is considered. Let us see the simulation commands. In serial mode, these are the commands which we need to use. Block mesh. This generates the multi-block mesh. Surface features identifies features in a surface geometry and writes them to file based on control parameter specified by the user. Snappy hex mesh command. This generates three-dimensional meshes containing hexahedra and split hexahedra automatically from triangulated surface geometries or tri-surfaces in STL or OBJ format files. Set fields command. This command set values on a selected set of cells patch faces through a dictionary. Then finally, the launch command is foam run. This launches the solver in serial mode. So in parallel mode, these are the commands. The first three commands are similar. Then we use decompose pair command. This command automatically decomposes a mesh and fields of a case for parallel execution of the OpenFoam. Then we use the MPI run command to launch the case with two or more processes. Finally, once the results are completed, the simulations are completed, we use reconstruct pair command. This command reconstructs fields of a case that is decomposed for parallel execution of OpenFoam. Now let us launch the case in serial mode. Now open terminal and set the path to the working directory. The first command is block mesh. So this is done. Then the second command is surface features. This is also done. Then the third command is snappy hex mesh. Okay, now this will take some time. So meshing is done. The next command is set fields. So this is done. Now let us first check the case files and see if all the boundaries are created properly or not. Now open 0 folder. Here we see a new file alpha is created. Now rest is fine. Let us open constant folder. So these are the new folders created here. Open this folder and see all the three STL files are updated here. Now in Polymesh, you see all the files. So open this boundary file and see if the boundaries are updated or not. So here we can see two wall boundaries, wall boundary, wall and object. So the meshing is done fine and the setup is okay. And in try surface, you can see the eMesh files created for all the three STL files. So now this is fine. We can now launch the case. The launch command is foam run and launch it. So here I have not updated the time. Okay. I go to system folder, open control dict. It should be 0. And rest is fine. Now I can launch the case. Now the simulation is started. Once the simulation completes 30 seconds, I will show the animations. The animation of first simulation is presented here. From 0 to 10 seconds, the capsule rotates in anti-clockwise direction, and from 10 to 20 seconds, the capsule rotates back in clockwise direction. From 20 to 30 seconds, the capsule oscillates in multiple directions. Simulation 2, object rotation. In this simulation, only object rotates and the capsule remains stationary. So let us see the simulation commands in serial mode. So here block mesh, I already explained this. So surface features, again the same, and these three commands remain the same. But here now, as the object which is enclosed in the capsule only rotates and the capsule remains stationary, so there is a stationary and a dynamic mesh. So the interface has to be separated, and then we need to create the boundaries there. So for that purpose, these two commands are used: create baffles. So this makes the internal faces into boundary faces, does not duplicate points. Now the next command, split baffles, detects faces that share points and duplicates the points to separate them. So these two commands will create the interface boundaries between the stationary and the dynamic mesh. Then renumber mesh. So this command renumbers the cell list to reduce the bandwidth, reading and renumbering all fields from all the time directories. Then we have to create the non-conformal couples, because in the interface there is a stationary boundary face and the rotating boundary face. So this needs non-conformality. So for this purpose we use this command, create non-conformal couples. This is a utility to create non-conformal couples between non-coupled patches. Then the command set fields, which is already explained, and we launch the case in serial mode using foam run as usual. In parallel mode, up to here set fields, the same commands are used. Then once this part is done, we use decompose pair to automatically decompose the mesh and fields of a case for parallel execution, and then use MPI run to launch the case in parallel mode. Then once the simulations are completed, the command reconstruct pair is used to reconstruct the fields for post processing. Now let us launch the case. Now before launching the case, let us modify the file dynamic meshdict in constant folder. In the earlier simulation 1, we have used the data file. Now we are going to use the direct syntax of rotation. So here this part we will change. Now this is the syntax for directly rotating the object by giving the angular velocity. So here the cell zone is cylinder, only the cylinder will be rotated, and the solid body motion function is rotating motion. So this is the center of rotation of the object. Here the origin which we are giving is the center of the object. Then the axis of rotation is in z direction, and the omega is 10 radians per second. Fine. Once this is done, now we'll try to launch the simulation. Now open the terminal and set the path to the working directory. The first command is block mesh. So this is done. Then the second command is surface features. So this is also done. The next command is snappy hex mesh minus overwrite. So this will take some time. So meshing is done. Then the next command is to create the baffles. Done. Then we need to split. Then renumber mesh. So after renumbering, we have to create the non-conformal couples. So this is done successfully. Then we have to create set fields. Before doing that, we have to do an important modification in the folder. So let us go there once again. To open this constant folder and go to polymesh. Open this file boundary. Now here you see the non-conformal non-coupled boundaries are created. We need to copy this part from here. Then now go to 0 folder, open U. Paste here. Once we have pasted it, we need to do small modifications. For non-coupled one, change the patch type to moving wall split velocity. Then we can remove these three and add value. The same we can copy and paste to the second one, that is non-coupled 2. Now further here we can delete this part. So we have made these modifications here. Now we can copy this part from this file and open this p_rgh file. Here add here. And then we need to modify. For non-coupled one, we have to change the type to pressure, and you can remove this part. Copy this and just change this to. And no need to change anything here. Once this is done, now copy this again from this file and open alpha water. Now here paste this part. Now we have to change the type for this here as 0 gradient. and change here and here. So, so now here everything is modified. Close this file now. Then you can go to terminal back and then use the command set fields. So now this is done. Then go back to the folder and open this 0. You can see the new file, water file is created here. Now everything is fine. We can launch the case using foam run. So the simulation has started. Once the simulations are completed, I will create the animation and present here. So here is the case 2 animation. The object is rotating with angular velocity 10 radians per second and the capsule is stationary. Simulation 3, object oscillation. In this case, the object oscillates and the capsule remains stationary. Simulation commands. The same commands used for simulation 2 can be used in this case. The case can be relaunched after the following modification in a file. In the case with object rotation, we have seen in the dynamic meshed file, the rotation is given. Open this file and make the following change. Now here we are adding this block here. So it is solid body motion function is oscillating rotating motion, the same origin, same axis of rotation, and we add another parameter amplitude with this value. So the amplitude is 10 in z direction with the same omega 10 radians per second. After making this change, just save the file and we can launch the case using the same simulation commands. Once the simulations are done, I will show you the animation. So here is the case 3 animation. The object is oscillating with angular velocity 10 radians per second and with amplitude 10. So finally I tried to explain the procedure to set up a proof of concept case with multiphase and dynamic mesh modules in OpenFoam12. Should you have any queries, don't hesitate to leave a comment. Please do like, share and subscribe, and do not forget to click the bell icon. Thank you for watching.